Hey everyone. So in this video, I like to go over some problems from the final review activity. And so there are quite a few problems, so let's just jump right into things, and I'll try to keep things rather quick. So here, this problem I like to start with is problem 2, where we're given a function g of x and we'd like to find the discontinuities. And so when can a function be discontinuous? Well, there's a few different ways. There's jump discontinuities, where the graph is sort of broken up. Maybe we're given a piecewise function and the pieces don't connect. Here we don't have a piecewise function, so I don't think we have to worry about that. We can have removable discontinuities where a point is plucked out. And so that occurs when maybe we have some fraction and there's a denominator of 0, but there's actually also the same factor that leads to that denominator of 0 is in the numerator as well. And so that discontinuity is kind of pulled out, can be sort of canceled out, or the factors can be canceled out. And then we get infinite discontinuities when we have denominators of 0, where the factors that correspond to that 0 denominator, those can't be canceled out. And so here, if we look at this function, we have fractions within fractions. And so whenever one of these denominators is 0, we're getting a discontinuity. And so here, when is this first denominator 0? When is x plus 2 equal to 0? So, well, that happens when x is equal to -2. What about e to the x? Is that ever 0? Well, no, that exponential function is never 0. It's always positive. So that doesn't contribute any discontinuities. And then e to the x minus 1, is that ever 0? Well, when e to the x is equal to 1, and then we have minus 1, that would give us 0. And so that occurs when x is equal to 0, right? When x is equal to 0, e to the x is equal to 1, and then we'll have 0 in the denominator of the larger fraction. Okay, so here let's move on to the next problem, problem 4a. So we're given f of x is equal to the square root of 9 minus x, and we want to find the derivative of this function. I'm not using derivative rules, but using the definition of the derivative, right? So this idea that we can take the limit as h approaches 0 of f of x plus h minus f of x all over h. So when you're asked to compute the derivative using the definition of the derivative, we're sort of using this idea, this sort of first principles idea, that we're kind of computing a secant line, but letting that secant line get closer and closer to the tangent line. And so this is that sort of limit. And so here let's go ahead and use this idea to evaluate the derivative, or find the derivative function of f of x. So here, we have our limit as h approaches 0 of f of x plus h. So here f of x is the square root of 9 minus x. So we have the square root of 9 minus x plus h. Right, so that's being replaced with x, and then we're going to be subtracting that x plus h away. So remember to distribute that negative. Then we have minus f of x. This is minus square root of 9 minus x all over h. And so here, we've kind of used some algebraic tricks in the past to deal with these kinds of expressions, so that we can somehow find a way to get rid of this h in the denominator that's approaching 0. So one trick we can do is we can multiply by the conjugate. We can multiply the top and the bottom by 9 minus x plus h plus 9 minus x underneath square roots, that is. And we can do that to the top and bottom of this fraction. Right, so this is just some nice algebra. It's multiplying by 1 in some special way, but it's a convenient way that simplifies the numerator in some way that allows us to get rid of this factor of h in the denominator. So here, when I multiply out the numerator, this is a difference of squares. Right, so here we'll have the square of the first term, which will be 9 minus x plus h. And then here we'll have take away the square of the second term, so 9 minus x, right? The square of the square root of 9 minus x underneath the square root would give us just 9 minus x. So here this would be h times square root of 9 minus x plus h plus the square root of 9 minus x. So one thing I should say is that we have to make sure that we're sort of keeping the limit along with each of our equalities until we actually evaluate this limit. Okay, so right now we have an equality of limits. Okay, so what can we do from here? Well, we can distribute some negative signs and combine some like terms. So here I have the limit as h approaches 0 of, this is 9 minus x minus h minus 9 plus x. I just distributed some negatives. And then in the denominator, I guess I could distribute one negative here to get 9 minus x minus h plus square root of 9 minus x. And so here we get an x term that cancels out, and the 9 cancels out. So we have this minus h in the numerator, and this factor of h cancels out, giving us just a minus 1 in the numerator, right? Originally it was minus h, and so when we cancel out that factor of h, we were just left with minus 1 in the numerator. And now we can let h approach 0. We can just evaluate h at 0 because this function is now continuous at h is equal to 0. So here I'll have negative 1 over, this is the square root of 9 minus x minus 0 plus 9 minus x. Well, here this minus 0 doesn't really contribute anything, and now we just have two equivalent terms in the denominator that we can add up together. We have minus 1 over 2 sets of 9 minus x underneath the square root. So this is the derivative function of f of x, and this is we compute this through the definition of the derivative. So now let's find some derivatives using derivative rules. So here, let's evaluate the derivative of y is equal to e to the x squared sine of x. All right, so here, this is a composition where our outer function is e to the x, and our inner function is, well, it's equal to x squared sine of x, right? So this is, our original function is just f composed with the g. And so we can apply the chain rule, and let's just kind of go through the motions of what the derivative of these outer and inner functions are. So f prime of x is equal to e to the x, and then g prime of x. Well, this is something that requires using the product rule because we have the product of two different functions of x, right? So here I'm going to take the derivative of the first part of our product, and multiply that with just the second factor. And I'm going to add that with the derivative of the second, so that comes out as cosine of x times just the first factor. And so here, if I want to evaluate our original derivative, maybe I'll just rewrite the chain rule, right? So here the derivative with respect to x of f of g of x, it's hard to count all those parentheses correctly, is just the outer derivative evaluated at the inside function multiplied with the derivative of the inside function. I think I overcounted parentheses there. Okay, so if I want to evaluate the derivative, if I want to find y prime, then we're going to take the outer derivative, so e to the x, evaluated at the inside function. So here we just get the same expression actually, right? So e to the power x squared times sine of x, and then we multiply it by this derivative of the inside function. Right, so here it's 2x sine of x plus x squared cosine of x. This is all multiplied with. Maybe I should move this to the side just to make sure we have enough space. So this is multiplied with 2x sine of x, and I think it was plus cosine of x times x squared. So I'm going to write that as plus x squared cosine of x. And here, I don't see any way that this is going to clean up all that well, so we can just leave it at that. Okay, what about 5c? So 5c, we're given the function f of x is equal to ln of x times ln of x. And so again, we have some inside and outside function. Right? So here's my inside, or my outer function is ln of x. My inside function is x times ln of x. And so here, maybe I'll just write, so I know I've called this original function f of x, but maybe just for the sake of simplicity, I'm going to just use f and g when I'm talking about the chain rule here. So our outer function is ln of x. Our inner function is, this is x times ln of x. And so when we want to evaluate the derivatives, well, we're going to need, the derivative of our outer function, that's 1 over x, and then the derivative of our inner function, well, it's the derivative of the first times the second, so this is 1 times ln of x, plus the derivative of the second times the first. So that'd be 1 over x times x, that'd just be just 1. Okay, so here if we want to evaluate this derivative, well, it's going to be 1 over, right, so the derivative of the outside, then evaluate at the inside function. So 1 over the inside function, so 1 over x ln of x. Then this is going to be multiplied with the derivative of the inside function. So this is going to be multiplied with, ln of x plus 1. And, there are some things we can do here. We can imagine, right, this would be in the numerator of our fraction. So we can imagine splitting apart this fraction across that numerator, across that sum. We have ln of x over x ln of x plus 1 over x ln of x. And this factor of ln of x would cancel out, and we would have 1 over x plus 1 over x ln of x. So this isn't really significant simplification. It's not something I would really grade you on. But sometimes there's some very nice simplification that can occur, and you should be on the lookout for that. Okay, so next let's deal with 5i. So here we're given y is equal to ln of 2x cubed. And so again, we want to use the chain rule here. Maybe I won't go through all of the motions because we've done it a few times now, but this is y prime is equal to, now we would take the derivative of the outside function. So this is the outside function is the cube function. We would apply the power rule. And so we would have still the same inside function. All we did was just apply the power rule, bring that factor of 3 down, decrease the exponent by 1. But then we saw that same inside function, ln of 2x. And now we have to multiply by the derivative of this inside function, which is, well, the derivative of ln of 2x is 1 over 2x. And this is again going to require the chain rule, because we still have to multiply this with the derivative of the inside function. This would be multiplied by the derivative of 2x, which is just 2. And so here, this factor of 2 in the numerator and the denominator would cancel out, and we would just be left with y prime is equal to 3 ln of 2x, and then all this is squared divided by x. So that's y prime. Now what about 5j? Well, this is a very similar looking function. We have p of x is equal to ln of 2x cubed. So it's a lot like our previous function, but the cube is not outside of the entire function. It's just, we're just cubing x inside the input. And so here this is a friendlier example of the chain rule. So here p prime of x, well here we would take the derivative of the outside function, evaluate at the inside function, so 1 over x, but instead of just x we have 2x cubed. And then we're going to multiply by the derivative of that inner function, so the derivative of 2x cubed, well that's 6x squared. And so this is equal to 6x squared over 2x cubed. We can cancel out some factors of x. Maybe I'll actually do this factor of 2 first. We're left with 3 in the numerator. This is 3 over x. So this actually simplifies quite nicely. So now let's take a look at this related rates problem. So here we're given a situation where we have a paper cup that's in the shape of an inverted cone, so a cone that's pointed downward. and we're given some information about this cone. So here, maybe I'll just draw a picture. It's always helpful to have something to visualize. So we have this cone. We're told that the height of the cone is 12 centimeters. So this measurement here, that's 12 centimeters. And we're also told that the radius of this cone, so the radius of the circle at the top, that's 4 centimeters. And so we know that water is being poured into this cone. It's coming in at a rate of 2 centimeters cubed per second, so a rate of change of volume. And we want to know how quickly the water level is rising when the water is 5 centimeters deep, right? So the idea is that water is being poured into this cup, and it's making another cone at the bottom of this cup. And we want to know how fast the height of this water is rising, specifically when this height is 5 centimeters, right? This cone at the bottom is 5 centimeters deep. And so how do we relate all of these different quantities together? Well, they're kind of what formula is out there that relates to the volume and the height and the radius of the cone together? Well, it's the formula for the volume of the cone, right? So V is equal to pi over 3 times r squared times h. And if we think about this water in the cone, it's forming another cone that's at the bottom, is its dimensions and its volume, they're changing as time goes on, right? This volume, this radius, and this height, they're all functions themselves. They're all functions of t, right? As time goes on and more water is getting poured in, all of these values change. And so here, when we work through related rates problems, and eventually we're going to want to take a derivative, we're going to take a derivative of this formula, and all these variables, we would have to apply the chain rule for, because they're all themselves functions of t. One thing that will make our lives a little bit easier, though, is that here, we have two different functions, r and h, that are themselves functions of t. And if we were to take the derivative now, we get some messy formula involving the radius, the height, the rate of change of the radius, and the rate of change of the height of this cone of water at the bottom. And that's a lot of things that we don't have all the information for. And so one thing we can do is we can sort of swap out r and h. So r and h are actually very related to one another in this cone, because r and h, we can see them as related through this similar triangle, right? So here, there's this triangle formed by the big cone, this right triangle, and there's this triangle formed by the smaller cone of water. And these triangles, they both have a right angle, they both share this bottom angle, and that means, this last angle will be the same. Right? If the three angles have to add up to 90 degrees, or not 90, 180 degrees in both of these triangles, and they share 2, well then that last one has to be the same. And so we can use the idea of similar triangles to say that, well, hey, if this is given by, if this is r in our smaller cone, and this is h in our smaller cone, well, we know that it shares the relationship that the corresponding sides are proportional between the two triangles, the two similar triangles. So here, that tells us that r over 4, right? So r, this side divided by this side length, is going to be equal to what we get when we take this side length and divide it by this side length, right? So here, this is 12 centimeters. So this is h over 12. And so this tells us that no matter what water level we're at in this cone, this is going to be the relationship between the radius and the height of the cone of water. And so here I can rewrite r as, well, I can multiply both sides by 4, giving us 4h over 12, or in other words, r is equal to h over 3. So this is the relationship between r and h, no matter what level of water we're at in this cone. And so here, if I look at this original formula for the volume of water, or the volume of a cone, in this particular cone, I can make the replacement R is equal to H over 3. And so V is equal to pi over 3 times R squared, but that's just H over 3 squared, and this is times H. So V is equal to, this is pi over, here we have H cubed, and then we have 3 sets of 3 in the denominator, so 27. And now we can take the derivative here. If I take the derivative, I have to keep in mind that V is a function of t and H is a function of t. So when I take the derivative of the volume with respect to time, or if I take just d dt of this entire equation here, that we get dv dt. Here we get pi over 27, and the derivative of h cubed with respect to t, well here, there's sort of this outer function of this cubing function. We would, bring that power down, and then we would decrement that power by 1, right? So here this would give us h squared. But then we have to take the derivative of this inner function, right? We've only taken so far the derivative of this outer cubing function. The inner function is, a function of t, and so here we have dh dt multiplied as well. And so here, now we have a new formula we can use, and we have some pieces of information for. We know the rate of change of the volume with respect to time, right? The water is getting poured in at a rate of 2 centimeters cubed per second, so this is just 2. We have the height of this cone. We're asked to find the rate of change of the water level when the water is 5 centimeters deep, right? So here we know that H is equal to 5. And so the only missing piece of information is this dh dt, and so we can solve for it. Right, so we have this equation, 2 is equal to pi over 27 times 3 times 5 squared times dh dt. And if we find dh dt, in other words, the rate of change of the water level, the height of the cone of water with respect to time, will be done. So this is 2 is equal to pi over 9 times 25. And so this is times dh dt. And so here if I multiply both sides by 9, divide both sides by pi over 25, or sorry, pi times 25. So this is 25 pi in the denominator. We get dh dt. So this comes out to be approximately 0.229 centimeters per second. So this is the rate of change of the height of the cone. So now let's look at 13b, where we're given all of these different conditions and we want to draw some sort of function that satisfies all of these conditions. So here f of x is less than 0, f prime of x is greater than 0, and f double prime of x is less than 0. This is on the interval from 1 to 2. Okay, so what does it mean for f of x to be less than 0? Well, this is telling us that really the function value, when we look at the function itself, it's going to be negative on this interval. So in other words, the function is going to be below the x-axis on the interval from 1 to 2. What does this mean? F prime of x is greater than 0. Well, this just means that the derivative of our function is greater than 0, and the derivative measures the slopes of the tangent line. So here, if we're saying that f of x is greater than 0 on this interval, and we're saying that the slopes of the tangent lines should be positive, or in other words, angled upwards. So here all this is saying is that our graph should be below the x-axis, but it should be sort of trending upwards from left to right on this interval. And then f double prime of x, well, this is just going to tell us the concavity. So here f double prime of x being less than 0, that's telling us that our function is going to be concave down. is going to open downwards, kind of like in this bowl shape, on our interval. And so here, if I kind of imagine our coordinate plane, so here maybe here's the interval from 1 to 2, so we're really looking at this interval here. So here we're saying that our graph should be below the x-axis. It should be negative, but it should be angled, or it should be angled upwards. So maybe it looks something like this. But if we did something like this, it wouldn't satisfy. It would satisfy the first two conditions. It would be negative. Our function would be negative. You know, it doesn't really matter what happens outside of this interval. We're only asking for it to satisfy the conditions on this interval from 1 to 2. So if this was our graph, it would satisfy the first condition that f of x is negative, right? It's below the x-axis. It would satisfy the condition that f prime is positive, because if we look at the tangent lines at any portion of this part of the curve, they would be angled upwards. It would be positive, but it would not satisfy this last condition that our graph is concave down, right? If we can see it in our picture, sort of bold upwards, it's concave up. The slopes of the tangent lines are increasing from left to right. And so here, this is not a sufficient graph. We want it to look something like, kind of like the left side of this picture, right? If we look at the left side of our concave down picture here, well, this is a portion of the picture that looks like it has positive slope, but is still concave down. So we want our graph to look something like this, but below the x-axis. It's going to look something like, let's say, it doesn't really matter what happens outside of our interval, but maybe it looks something like this. Right, so on our interval, the graph is negative, the slope is positive, right? The slopes are angled upwards, it's going from left to right, it's trending upwards, but it's concave down. You can kind of see that the slopes of the tangent lines to our curve, they're decreasing from left to right. It's concave down, the graph is bold downwards. Okay, so let's take a look at problem 16 now, where we have f of x is equal to negative 2x cubed minus 3x squared plus 12x plus 5. So here we want to find all sorts of different things. We want to figure out when this function is increasing, the intervals for when this function is increasing, when it's decreasing, where the local extrema are, so where the local minimums and maximums are, when this function is concave up, when it's concave down, the inflection points, and then we want to use all of this information to graph the function, to sketch some sort of graph. And so let's start with intervals of increasing and decreasing and the local extrema. So all this information can be found by taking the first derivative, examining the first derivative. So here let's evaluate, let's find f prime of x. Well, here I could just use the power rule, right? We get negative 6x squared minus 6x plus 12. And this is really equivalent to, if I factor out the negative 6, we get x squared plus x minus 2. And this is the same as negative 6 times x plus 2 times x minus 1. So this is the derivative function. And we can see that the critical points when this function is 0 occurs when the factors are 0. So x is equal to negative 2 and x is equal to a positive 1. These are the critical points, and are the places where we might have a local minimum or a local maximum. But maybe let's not focus on this for now. Let's focus on the intervals of increasing and decreasing. All right, so here, if I kind of sketch out a little bit of a number line, and I'm looking at an x value of negative 2 and an x value of 1. And so here, if I'm kind of imagining this number line as describing when our slopes are positive, negative, and 0, well, here I know that these points here are when we have a derivative of 0, right? Possible local maximums and minimums. And so what about the intervals of increasing and decreasing? You know, outside of these 2 points, we're going to have either our derivatives are going to be positive or negative. Right? We've already figured out when the derivatives are 0. Now we just have to figure out when the derivatives are positive and negative to figure out when the function is increasing or decreasing. And so here on this interval, is the derivative positive or negative? When we're looking at x values less than -2, are the derivatives positive or negative? So if I imagine plugging in some really large negative number into our derivative function, right, this factor will be negative, right? If I plug in like -100, this factor will be negative, this factor would be negative, and this factor would be negative. And if I multiply 3 negative things together, my result is going to still then be negative, right? So here, f prime of x is less than 0 when we're looking at x values less than -2. And so this is telling us that our f function, right, when the derivative is negative, the original function is decreasing. Right? The slopes of the tangent lines are negative. That's telling us that the original function is decreasing. Now what about if we kind of do the same reasoning but with really large positive numbers? If I plug in a positive number, if I'm looking at, really on this right side of my graph, or my number line, where I'm looking at really far positive numbers, well, this factor is going to come out positive, this factor is going to come out positive, but then this factor is still negative. Right, so if I have 2 positive numbers and I multiply with a negative number, I'm still going to get a negative number. F prime of x is less than 0 when we have x values greater than 1. And so this tells us again that f of x is decreasing. And then lastly, if I look at the same derivative function, but I instead plug in something in between -2 and -1 to figure out what this interval is like. Is the function increasing or decreasing on this interval? Well, here the derivative, if I plug in something like x is equal to 0, right? That's a number that's on this interval. Here we get 2. Here we get -1. So a positive number, a negative number, and then that's multiplied with another negative number. And so if I have a positive number and 2 negative numbers multiplied together, well, my result's going to be positive. So f prime of x is greater than 0 on this interval. And so f of x here is increasing. And so here, if I have my function is decreasing to the left of x is equal to -2, then it's increasing afterwards, that's telling me that my function has a local minimum at x is equal to -2. And then if my function is increasing before x is equal to 1 and then decreasing after, well, that's telling me that my function has a local max at x is equal to +1. And so what are the values of the local min and the local max at these points? What are the y values here? Well, we just have to plug these into our original function to find the actual points. So here, when x is equal to -2, so let's evaluate. So let's evaluate f of -2. So here, this gives us -2 times, well, -2 cubed gives us -8. Then -3 times -2 squared, that's +4. And then plus 12 times -2, then plus 5. Right, so this is going to give us the y value at our local minimum. And so this is +16 minus 12. This is then -24 plus 5. So this comes out to be 4 minus 24, so that's -20 plus 5. This is -15. So all that to say that this local minimum is at the point x is equal to 2, y is equal to -15. And if we do the same thing to find the y value at x is equal to 1, well, we just have to plug in 1 into this function. And here, if I plug in 1 into our function, then we're just going to add up the coefficients, right? Negative 2 times 1 cubed, that's just negative 2. Negative 3 times 1 squared is just negative 3. 12 times 1 is just 1. So we're just going to add up the coefficients, and this is negative 2 minus 5, that's negative 5. And then I see this positive 5 here would cancel out with that, so that'd be 0, and just be adding up 12. And so here, y is equal to 12 when x is equal to 1. Okay, so we found the intervals of increasing, we found the intervals of decreasing, we found the local extrema, their y values as well. Now we have to figure out when this function is concave up, when it's concave down, and what are the inflection points if there are any. And so that means we need to find the second derivative. So here we have our first derivative function. Our second derivative is equal to, well, here we would have negative 6 times 2, that's negative 12x, and then we have minus 6, and then plus 0, right? So here this is our second derivative function. F double prime of x is negative 12x minus 6. I'm going to rewrite that down here. F double prime of x is equal to negative 12x minus 6, and we want to find possible inflection points. So let's find the zeros. I'm going to factor out negative 6 to give us 2x plus 1. And so here we get a 0 of our second derivative when our factor 2x plus 1 is 0. This occurs at x is equal to negative 1/2. So if we draw out our sort of little number line for the second derivative, when it's positive, when it's negative, we know it's 0 at x is equal to negative 1/2. The second derivative is 0 when x is equal to negative 1/2. And so to the left and to the right, we just have to figure out whether those are positive and negative. And now if I look at this function here, and I plug in a really large, maybe let's do the factored form actually. So if we plug in a really large positive number into x here, well, that factor is going to be positive, but then it's multiplied with a negative number. So at the end of the day, on the whole, it's going to be negative. So on the right side, when we're looking at larger positive values of x, f double prime of x is negative, right, less than 0. So this is where the function as a whole, the original function f of x, it's concave down. And then what about when we plug in really negative numbers into our function? Well, here if I plug in a really negative number like negative 100, this factor is going to be negative. Multiply with negative 6, it's going to be positive at the end of the day. So f of double prime of x is greater than 0. Here we're looking at concave up part of our function. F of x is concave up on this interval. And so here, if our graph is concave up, and then it changes to concave down at x is equal to negative 1/2, that's telling us that this point is an inflection point. Right? Inflection points are where our function changes concavity. And so here, we're looking for the actual point, the location of this inflection point. We know the x value. What's the y value? Well, we're going to take our function and figure out the y value, find the point itself, right? So we're looking at f of negative 1/2. And so, the original function, that was negative 2 times our input cubed, so that's negative 2 times negative 1/2 cubed, that's negative 1/8. Minus 3 times negative 1/2 squared, so that's 1/4. Plus 12 times negative 1/2 plus 5. So this is 1/4 minus 3/4 plus, no, not plus, minus 6 plus 5. So here this is, what is this? This is minus 2/4 or minus 1/2. And then minus 6 plus 5, that's minus 1. So this is minus 3/2. So our point, our inflection point, is negative 1/2 comma minus 3/2. And so now we really have everything we need to sketch a good graph of this function. Right, so we were told, we found, actually, that we have an inflection point at, I'm just going to draw a really rough picture here, at -1/2, -3/2, so maybe down here. At -2, -15, we have a local minimum, so maybe down here. And then at 1, 12, we have a local maximum, so maybe up here. And to the left of this inflection point, we've got a concave up function, and to the right, we've got a concave down function. So here, this is a rough sketch of the graph. And it makes sense, right? To the left of this minimum, we saw that our function was, decreasing. To the right, it's increasing. To the left of this local maximum, the graph was increasing and then decreasing. And we saw that around this inflection point, to the left, the graph is concave up. To the right, the graph is concave down. And really, this is everything we figured out from our derivatives. So now let's take a look at problem 19. So we're asked to find the smallest possible product of two numbers, such that those two numbers, when we take their difference, is equal to 100. So here, we have two numbers we're multiplying together. I'm going to call P the result of this product. And all we know is that when we take the difference of these two numbers, we get 100. And so here, we're trying to find the smallest possible product. We're trying to minimize this product, minimize this product. And so we want to take some sort of derivative, find some critical numbers, and see, where the minimums are of this function. But here, we're not very used to taking derivatives of multivariable functions. So here, let's rewrite this function so that's just in terms of either x or y, just one variable. And the idea is that we can use substitution, right? So if x minus y is equal to 100, that means that x is equal to y plus 100 if we add 100 or y to both sides. And so that tells me that I can replace x in my equation with y plus 100, y plus 100. So that's x, and then it's being multiplied with y. And so actually here, I called our equation above, I called it p is equal to x times y. Well, now it's just a function in terms of y, so I'm going to write p of y. P of y is equal to y plus 100 times y, which is the same as y squared plus 100y. Okay, so this is now just a function in one variable. If we want to find the minimums, we should take the derivative, find the critical points, and check that that critical point is, or where the critical points are minimums, correspond to minimums. And so here, let's take the derivative of this function, p prime of y, and that's going to be 2y plus 100, which I can factor as 2 times y plus 50. So here we get a critical point at y is equal to negative 50, right? That's what makes this derivative 0. And so this is a candidate for a minimum. But we have to check that this is truly a minimum. And one way we can check is we can use the second derivative test, right? So p double prime of y, that's equal to 2. And here, this being 2 tells us that it's always 2 for whatever value of y. We've got 2 as our second derivative. Our original function is concave up. And so we can imagine our function, just a rough sketch of our picture is, maybe looking at some sort of concave up function. We found the minimum, or not the minimum, we found a critical point at x is equal to negative 50. And what we're really saying here is that because this function is concave up, and because this function is concave up, this critical point corresponds to a minimum, right? Where this derivative is 0 is right at this bottom point here. It's a minimum. Okay, so here, this is the y value that minimizes our product, minimizes. And so what does that make x? So I know, we're told that x plus, or x minus y is equal to 100. In other words, x is y plus 100, so that makes x equal to 50. And so our product is, the product of these two numbers. So the product, well, this is equal to, so this is negative 2,500. Always have trouble with multiplying values with a handful of zeros. It should be easy, but for some reason my brain just doesn't quite see it so clearly. But yeah, so negative 2,500 is this product. This is the minimum product that we can get from two numbers that sum, or their difference is 100. So let's do one last problem. We're given some function f of x. It's 4 times the square root of x minus 6x squared plus 3. And we want to find its antiderivative, f of x. So we want to find f of x such that f of 0 is equal to 7. So we want to find some antiderivative of this function, but specifically the one where when we plug in 0 for x, we get 7 out as our output. Okay, so how do we find the antiderivative of this function? Well, here, maybe it'll be easier to find the antiderivative if I rewrite the square root as x to the 1/2, right? So now, if I want to find the antiderivative, or in other words, the function whose derivative gives me f, I have to just reverse the power rule, right? I just have a bunch of different power functions added up together, so I can just unwind the power rule to find some sort of original function whose derivative would give us f, lowercase f. And so when we do that, typically when we have the power rule, x to the power n, and we take the derivative, what do? Well, we multiply by that exponent, and then we subtract 1 away from the power, right? So here we have x to the n minus 1. And so if we're going to find the antiderivative, then how should I write this? Let's say, so if I want to find the antiderivative of x to the n, well, we should sort of unwind this, right? So, the first step was multiply by the exponent. The second step was decrease the power by 1. To do this in reverse, we should also do the steps in reverse, right? So here this is going to take x to the n, and we're going to add 1, and then divide by this power. So this is going to be 1 over n plus 1. Or we can check that this is the reverse by taking the derivative of this and seeing that we get back x to the n, right? If I take the derivative of x, 1 over n plus 1 times x to the n plus 1, if I bring down that power n plus 1, it would cancel out with that division by n plus 1. And so that we wouldn't have that coefficient there anymore, we just have a coefficient of 1. And then taking 1 away from the exponent would give us just n. So this reverses the power rule. And so let's do that. Let's apply this idea. Again, maybe I should say the order. This is sort of first, when we're taking the antiderivative, and then this is second. So here, the antiderivative, I'm going to add 1 to our exponent. So adding 1 to 1/2 gives us 3/2, and then I'm going to divide by that exponent. So dividing by 3/2 is the same as multiplying by 2/3. So 4 times 2/3, that's 8/3. Next we have x squared, which we're going to raise the exponent by 1, divide by that exponent, so 6 divided by 3, that's minus 2. And then lastly we have 3, the antiderivative of 3 is going to be 3 to the x, right? I can kind of imagine this as 3 times x to the 0, and if I raise that exponent by 1, I have x to the 1, dividing by that exponent is dividing by 1, so I just have 3. But then, whenever we're taking the antiderivative, we're looking at the general antiderivative first. So any constant could be at the end here, and we would have a valid antiderivative of our original f function, right? Because when we take the derivative of this function, that c term would cancel out. Right? Derivatives of constants are 0. And so now we just need to figure out what the right value of c is so that when we plug in 0 into this function, we get 7 out. And so here, if I take f of 0, we're going to have 8/3 times 0 to the 3/2 minus 2 times 0 cubed plus 3 times 0 plus c. And all of these terms would cancel out to tell us that c, the only possible value of c here, so that we get 7 out at the end of the day, is equal to c. So here, what we have is that f prime of x is equal to 8/3 x to the 3/2 power minus 2x cubed plus 3x, and we just figured out that c needs to be 7 itself. So that's the antiderivative that satisfies the given condition.